So in this segment, I'm going to introduce the task of information retrieval, including in particular what's now the dominant form, web search. The task of information retrieval can be maybe defined as follows: that our goal is finding material, which is usually documents, of an unstructured nature, usually text, that satisfies an information need, that's what the person is looking for information on, from within large collections, usually stored on computers. So there's lots of mentions there of prototypical cases, and other kinds of information retrieval do exist. So there are things like music information retrieval, where there are sounds, not text documents. But effectively, what we're going to talk about here is the case where all of those usually clauses hold. There are many scenarios for information retrieval. The one that people think of first these days is almost invariably web search, but there are many others. So searching your email, searching the contents of your laptop computer, finding stuff in some company's knowledge base, doing legal information retrieval to find relevant cases for a legal context or something like that. It's always been the case that a large percentage of human knowledge and information is stored in the form of human language documents. And yet there's also for a long time been something of a paradox there. So this is just a kind of a not quite real graph to give a flavor of things. Don't really believe the numbers on the left-hand side are exactly what they mean. But what we're showing is that in the mid-1990s, it was already the case that if you looked at the volume of data, that there was some data that was in structured forms. By that I mean things like relational databases and spreadsheets, but there was already vastly more data in companies, organizations, and around people's homes that was in unstructured form, in the form of human language text. However, despite that, in the mid-1990s, structured data management and retrieval was a developed field, and there were already large database companies, where in the field of unstructured data management, there was very little. There were a few teeny little companies that did various kinds of corporate document retrieval and things like that. That situation just completely changed around the turn of the millennium. So if we look today, the situation is like this. So the data volumes have gotten larger on both sides, but in particular, they've gotten larger on the unstructured side with a massive outpouring of blogs, tweets, forums, and all those other places that now store massive amounts of information. But there's also then been a turnaround on the corporate side. So now we have huge companies that are addressing the problems of unstructured information retrieval, such as the major web search giants. So let's start and just say a little bit about what is the basic framework of doing information retrieval. So we start off by assuming that we've got a collection of documents over which we're going to do retrieval. And then at the moment, we're going to assume that's just a static collection. Later on, we'll deal with when documents get added to and deleted from that collection and how we can go out and find them in something like a web search scenario. Then our goal is to retrieve documents that are relevant to the user's information need and helps the user complete a task. Let me go through that once more a little bit more slowly with this picture. So at the start, what we have is that the user has some task that they want to perform. Let's take a concrete example. Suppose what I want to do is get rid of the mice that are in my garage, and I'm the kind of person that doesn't really want to kill them with poison. So that's my user task that I want to achieve. And so to achieve that task, I feel that I need more information. And so this is the information need. I want to know about getting rid of mice without killing them. This information need is the thing with respect to which we assess an information retrieval system. But we can't just take someone's information need and stick it straight into a computer. So what we have to do to be able to stick it into a computer is to translate the information need into something that goes into the search box. And so that's what's happened here. We now have a query. And so here's my attempt at a query. How trap mice alive. So that's taken this information need and I've made an attempt to realize it as a particular query. And so then it's that query that goes into the search engine, which then interrogates our document collection and leads to some results coming back. And that may be the end of the day, but sometimes if I'm not satisfied with how my information retrieval session is working, I might take the evidence I got from there and go back and come up with a better query. So I might decide that alive is a bad word and put in something like without killing and see if that works any better. Okay, what can go wrong here? Well, there are a couple of stages of interpretation here. So first of all, there was my initial task, and I made some decisions as to what kind of information need I had. It could be that I got something wrong there, so I could have misconceptions. So maybe in getting rid of mice, the most important issue is not whether or not I kill them, but whether I do it humanely. But we're not going to deal with that issue so much. What we're more interested in here is the translation between the information need and the query. And there are lots of ways in which that can go wrong in misformulation of the query. So I might choose the wrong words to express the query. I might make use of query search operators like inverted commas, which might have a good or a bad effect on how the query actually works. And so those are choices in my query formulation, which aren't altering my information need whatsoever. That's important when we talk about how to evaluate information retrieval systems. That's a topic we'll say more about later, but let me just give you the first rough sense of this because we'll need it for everything that we do. So whenever we make a query to an information retrieval system, we're going to get some documents back and we want to know whether the results are good. And the very basic way in which we're going to see whether they are good is as follows. We're going to think of two measures which are complementary, one of which is precision. So precision is the fraction of the retrieved documents of the system that are relevant to the user's information needs. So that's whether when you look at the results, it seems like 1 document in 10 is relevant to the information need you have, or whether 7 documents in 10 are. That's assessing whether the mix of stuff you're getting back has a lot of bad results in it. The complementary measure is the one of recall. Recall is measuring how much of the good information that's in the document collection is the system succeeding in finding for you, at the fraction of relevant docs in the collection that are retrieved. We'll give more precise definitions and measurements for information retrieval later, but the one thing I want to express right now is that for these measures to make sense, they have to be evaluated with respect to the user's information need. For certain kinds of queries, such as the ones we'll look at in the following segments, the documents that get returned are deterministic in terms of what query is submitted. So if we were just going to evaluate what gets returned with respect to the user's query, then we'd necessarily say that the precision is 100%. But that's not what we do. What we do is think about the user's information need, and that the precision of the results is assessed relative to that. So in particular, if we just look back for a moment, if there's been a misformulation of the query by the user, or just they didn't come up with a very good query, that will be seen as lowering the precision of the returned results.
data types that we hear so much about today in storage. They go by a variety of names, but I think they're probably most commonly referred to as structured and unstructured data. The first question that I think whenever I hear a new term put out there is, well, why do I care? The answer in this case turns out to be because the growth model for the two data types is so dramatically different. This graph is by IDC, which depicts storage usage over time, breaking out structured and unstructured data. In this particular case, structured is labeled block and unstructured is labeled file. What's striking, of course, is that the unstructured data has a growth curve substantially greater than that of structured data. If we look out to 2014 projections, we see that combined the forecast is to ship 80 exabytes of storage, where an exabyte is 10 to the 18th or a million billion. So it's a big number. It also shows that the lion's share, almost 70 of this 80 exabytes, is expected to come from unstructured data. So you're getting close to saying 90% of all storage shipped in 2014 will be to store unstructured data. That's a big enough difference to qualify as a substantial shift in the storage industry. And it doesn't really matter which side of the equation you're on, whether a producer or consumer of data. Change of this magnitude, I think it warrants a look under the covers to see what it's all about. And that's what we'll be doing in this session. Okay, let's move on to the definition of these terms. The term structured is really meant just to indicate a database. And what does a database look like inside? Most people haven't written database code, but they have used Office applications where spreadsheet tools like Excel for Windows and Numbers on the Mac. Those tools allow you to create simple database tables. In this particular example here, you have customer records with the typical information such as name, address, etc. And that's it. You've created a database table. And while sophisticated DBMS systems allow you to do much more than you can do with a spreadsheet, the base concept is essentially the same. It's simply tables with rows and columns, most often containing straight ASCII text, as we have in our example here. For many databases, you access the data via a language called SQL or SQL, which stands for Structured Query Language. SQL provides a well-defined way for applications to be able to manage their data in the database. I've added a little snippet of SQL code here that illustrates how an application could retrieve, for example, all rows from a table called book where the price is greater than $100 and returns the results sorted in ascending order by title. With unstructured data, we have far greater variety, since we've defined unstructured data as everything that is in a database. We can start with basic Office documents that most users work with today, such as word processing documents, presentations, etc. They're probably the most familiar document type to the average computer user. However, it's true that these file types, they've certainly increased in size over time as it gets easier to embed things like digital images into say, a Word document. Still, there's no way that that's going to eat up 70 exabytes of storage that we saw in the projection a couple slides back. So there has to be something else out there that's using a bunch more storage, and that's where rich content comes in. Rich content includes things such as music files, digital pictures, full motion video. And these rich data types require a lot more storage than does text. Moving beyond the common Office file formats, many verticals have a growing slate of rich data themselves, whether it's the form of X-rays or MRI scans in the medical space, or the massive amount of data that we see generated in the oil and gas vertical. The larger point, I think, is that in each vertical, we're seeing more and more rich content being produced. To illustrate just how dramatic a difference the rich data world is over the ASCII text, let's look at the difference in a very common activity. Say you decide, I want to go to the movies. How do you decide what to go see? Well, it wasn't too long ago that the only option available to you was to go and read movie reviews and judge by that. Here's a review in the Boston Globe for a movie in theaters now. It's called Real Steel. It's a movie set 9 years from now in 2020 where humans no longer fight in the ring, but giant robots do the boxing instead. So you can try to get a sense of the movie by reading this text. Alternatively, today you can download the movie trailer itself, and let's see if that gives you a better sense of what kind of movie this is.
Fighting has changed. But the crowd, they never change.
Our main event tonight features pain!
They just get bigger. The human body can only take so much. But the steel never stops.
So there you go. I think we can safely label a few things as obvious. One, most of us would prefer rich data over basic text in most cases. Two, rich data takes up way more space than basic text. The text of the movie review, when I downloaded it, 10,000 bytes of disk space. The movie trailer in HD, 200 megabytes. That's an incredible difference. We're talking 20,000 times more storage capacity required to do the movie trailer than for me to read the review. If you jump back to slide 3, one of the things I look at whenever I see these type of projections is I try to do a basic sanity test. One question that came to mind is, does this 6x multiple of unstructured data versus the structured, does that feel right? And at first glance, it felt like too big a jump to me. So I was a bit suspicious. But when we dive in and look at an example like that movie trailer where you have a 20,000x difference, that's just one example, but at least it gives us a quick sense of how an analyst might arrive at that 6x spread when they look at everything in aggregate. Okay, so finally, we could say that at least in certain applications, it's probably fair to posit that rich data use is increasing at an increasing rate. Or said differently, we could rationalize the case for exponential growth in certain sectors. Now, of course, it's hard to extrapolate growth trends from there, but let's leave that work to the analyst community. They get paid to create those models. From our perspective, we can at least just get a sense of how dramatic the difference can be. And this is the type of change we're seeing in the storage industry in this decade. It's a pretty dramatic difference than what we've seen in prior decades. And we've seen some of the reasons why we're seeing this.
Yuan has already done an excellent job of discussing what vectors mean to information retrieval. So I thought the more interesting question to discuss for this mini lecture would be, how did we get here? How did we get from card catalogs and the early stages of information retrieval with concordances and indices. How did we move into vectors, which is what we're talking about today, and what does that mean? And then finally, how did all of that work finally lead up to the incredible importance that full-text search brings to us today? So that's what I'd like to talk to you about today. Our first step in our history of information retrieval is Moore's Law. No, I didn't spell it wrong. This is a different guy. This is Calvin Moore. He coined the phrase information retrieval at a conference paper in March of 1950. He also invented something called Zoto coding, which is an indexing system using punch cards. Keep in mind that at this point in time we're talking about using computers to index paper. That is where we're at. So, along with the indexing these papers, one of the earliest contributors to creating a really interesting way of doing things was Hans Lund, that really has an enormous impact on our world today. He invented QUIC, which is a keyword in context algorithm. It was basically a concordance, an inverse index. But the interesting part is that he thought to display the indexed word in context. You found such and such thing in an index, but then it also showed you the word surrounding it. That way you can make a better determination over whether what you are looking for is in this paper or is not in this paper, based on what surrounds it, and not just the fact that the word exists there. This was the first real attempt to do something interesting that has kind of followed through to modern day. You've certainly seen that in your 10 blue links. So we have a lot to thank Hans Lund for. Next we move on to the fellow that wrote the paper that we're discussing today, Gerald Salton. Gerald Salton is probably the most important early pioneer of information retrieval. By creating vector-based text indexing, he allowed mathematical principles to be applied to data. He allowed us to search data in a mathematical way and apply all sorts of different algorithms and techniques that are known to produce important results. And this insight has pretty much shaped modern information retrieval. Bear in mind, at the time he's still talking about indexing papers, so the absolute importance of his work probably wasn't recognized at the time. But pretty much we live in the world that Gerald Salton has created. He also won the Gerald Salton Award, which is a pretty neat trick. Although at the time, of course, it was called the SIG-I Award for Outstanding Contribution to the Study of Information Retrieval. So, well done, Gerald. All of those previous examples and figures were all about the time before we had the web. Now that we have the web, they thought they were drowning in information then. Well, you know where we're at today. With the web, search engines became an essential part of our everyday lives, and it really brought the principles of information retrieval to the masses. Now, it's not only something that your science geek looking for a particular chemistry paper on his subject is going to be interested in. Now my mother is doing information retrieval. Early players in this search engine was Yahoo, was very important, but they did everything by hand. And then came along Google, who remembered their math. As you probably realized, PageRank is basically an adaptation of vector-based searching. And I've already pointed out how QUIC contributed to the display of search results for Google. So basically you can say they won the war by paying attention to the past.